Okay, welcome back to the tutorial on OpenFringe. This is part 2, where we're going to analyze an interferogram. Before you can analyze an interferogram, you have to tell OpenFringe what the parameters of the mirror are. Do that by going to the configuration menu, and under there, the very first item is mirror test parameters. In the mirror test parameter dialog box, you can type in information about the mirror. In this case, I called it ESON 8. It's a mirror that, of course, this is already a dialog I had filled in. You can select either in millimeters or inches, and you can select. You need to select the diameter of the mirror, and then either its radius of curvature or its F number. If you want to put an obstruction in there, maybe you have for have a 1-inch diameter obstruction, you'd type a 1 in there. In my case, the mirror is a parabolic mirror, and its conic constant then would be -1. OpenFringe can analyze non-parabolic with other conic constants. The other thing you need to enter is the interferogram wavelength. In my case, I used a red laser pointer who has a wavelength of 635 nanometers. For most testing, the artificial null checkbox should be checked. You don't check it when you're testing a sphere or when you have optical nulling components in your test path, like a double pass setup using autocollimation or some sort of other nulling system. The rest of this you can leave blank if you don't have a double pass setup. After you have the dialog set, you can click Save in a file, and it will save the file with the .ini extension, and I've already got mine saved as ESON 8, so I'm not going to overwrite it, but I could save it right there. Or you can go read an existing file. Once you have input a file to OpenFringe, the next time you open OpenFringe, it will remember what file you last had, what mirror you were last testing, so you don't have to keep continually adding that. OpenFringe has several methods of analyzing interferograms. One of them is called FFTAnalysis. In that mode, you don't have to actually draw any lines and trace any fringes in the interferogram. It's the simplest of all the interferogram analysis. It also can give a lot more detail, and I find it a lot easier to use and gives me more accurate edge information than fringe tracing. So I'm going to demonstrate how that is done, the FFT analysis method is done. So first we need to open an interferogram for the mirror that we just put our configuration in. Go to the Files menu, click the Open. A dialog will open that will show you all the image files. They can be JPEGs, TIFFs, PNGs, bitmaps, and so here's a JPEG image with quite a few fringe lines on it that's needed for FFT analysis. So let's open that one. Now I have had to reduce the size of the OpenFringe window a bit so that the video that I'm making isn't very big. Normally this would easily have opened in a window and you wouldn't get scroll bars. But that's okay, we can still handle it the way it is. The next thing we need to do once we have the image of the interferogram loaded is we need to outline the edge of the mirror so the program knows where the mirror is in the image. I like to do that by using this cursor and selecting a point on one side of the mirror, then select a point on the other side of the mirror, trying to get about halfway across the mirror, or across the diameter of the mirror, and then from there I select the Edge and Edge button over here from the control side, and it draws a circle around through those 2 points. And you can't see it in this particular image, but there is an expanded view that's being displayed wherever the cursor is, and you can then use that view to see how much better, to see how well you've circled the mirror. We'll assume right now that I've got it circled pretty well. Let's take a closer look at some of the controls we have over here on the right side. This is called the Edit Ellipse control, and at this point, when we just have an interferogram loaded, this control will pop up, and in our case we have selected to edit an outside ellipse. I could also select an inside ellipse to edit, and I'll just stick one here to show you, and I will do an edge and edge on that one, and there is the inside ellipse. I can then erase that ellipse, and it will erase whatever ellipse was selected in this control. So I'll have the radio button now is the outside ellipse, and the obstruction ellipse is now gone. You can fine-tune the position of the ellipse or the circle after it's drawn by using the arrow keys and the Shift minus and the Shift plus key. Here I'm using the down arrow key to move the circle down to have it cover the outline better. I can use the Shift right key, which I'm doing now, to move it over to the right, or Shift left key to move it to the left. I can use, I'm sorry, I said Shift up and down, just it's the arrow keys without Shift. But if I want to reduce the size of the circle, the diameter of the circle, I can do Shift minus, which I'm doing right now, and slowly shrink the diameter of the circle, or Shift plus, and we'll expand the diameter of the circle. Okay, now that we have the interferogram outlined, let's go on to the interferogram FFT analysis. That's the tab right here. Select that. It again shows the interferogram, and we have a new set of controls down the side here. Then we proceed from top down using them. The next thing I like to do is I like to resize the image down to 640 by 640. That will resize just the mirror part down to 640 by 640, throw the rest of the interferogram away, and create a smaller analysis file and take shorter analysis time. So all you have to do to make that happen is click on this center and resize image to 640 by 640 button. Now that I have done that, the next step is just to click on the FFT button. We'll compute that. It's getting a little bit small to see here, but in the center there will be a blue circle, and we want to enlarge that blue circle until it gets close to the first 2 white circles. So this part of adjusting the blue circle size is no exact science. You just it's kind of a variable control, and it helps filter out some of the noise, the fringe print through that might happen from the interferogram onto the surface. We're still going to get some, and we'll talk about that later. The next thing you do after you have the center spike mask set is then you press Compute Surface. The first window that pops up after the analysis is a contour display to see if there are any unwrap errors. We don't get that much when you have a very good interferogram like I had, and so I'm not going to describe that right now. We can see because I put a diagonal obstruction in the config menu in the mirror, it says it's not going to analyze that part of the mirror. So let's select the surface data now, and we'll get a 3D image by clicking this button. FFT analysis can create quite a bit of extra noise into the surface analysis that is shown up by these spikes around here. Once we average several of these together, the spikes go away. But there's also another way to get rid of them, and the first way to do that is to go from the FFT wavefront, but to fit a series of Zernikes values to that same wavefront. This gives us an analysis and resolution at least as accurate as a fringe tracing, but with higher resolution across the whole surface. Surface plots here are not the actual surface of the mirror, but they represent the air of the mirror. If the mirror was absolutely perfect, this would be a flat, plain surface. Another way to look at the mirror besides a 3D display would be to look at a profile across the diameter of the surface. We can do that here by clicking on the profile button here. This adjuster adjusts the angle that it looks at through the mirror. Here's the center of the mirror, here's the left side, and here's the right side. We can see the amount that the surface deviates from a perfect surface. We can spin the diameter around and look at various parts of the mirror that way. This is a wavefront air, and we can change it down to surface air by pressing this button. Let's go back to the 3D display and take a look at what else is available in the display here. We can see what the conic constant is of the mirror. This one's a minus 0.976, so it's just slightly undercorrected. It's not all the way corrected as a 0.1 mirror would be. Here it has a straw ratio of about 0.936. Another way, besides using the Zernikes polynomials to smooth out the mirror surface, let's go back to the wavefront display. We can use a Fourier transform mechanism of a low-pass filter. If you click on this button here, it provides a filter of 0.06, which I find gives a pretty reasonable display. So let's apply that. There we see the surface. It's a little bit bumpier than in the Zernikes based surface. We see artifacts of what we call fringe print through. If we had fringes closer together, they tend not to print through onto the surface. But it still gives us a pretty good idea of what the mirror is. We notice now the straw has dropped a bit because we do have this slightly rough surface from this, but the conic constant has figured out is still the same. One of the things you can do here is, or in the Zernikes based surface, is we can go off to simulations and look at create simulated Foucault displays. This Foucault data is created from the data we were just looking at, and we have a place here where we can set the knife offset, which defaults to being set at 0. We can also change it to a moving or non-moving surface, and let me change the knife offset to a value of 0.01, which will start moving the knife away a bit. We can see that it looks like performs like a real Foucault test. I'll move away a little bit more, 0.02. Maybe even 0.06. Now we have just the edge zone. Probably we can put a mask on the mirror and see which zone looks like it might be nulled. And it looks like perhaps the null is just a little bit past the far edge zone on this mask.